Welcome to the class of differential equations and matrices. And this time we are moving to chapter 8. It's Laplace transforms. Basically, we are going to use the Laplace transform to solve differential equations. So now we are at 8.1 Laplace transform. And let's take a quick look. What is a Laplace transform? Here's my first example. It is an integral. And I hope you remember there's infinity sign as the upper bound for the integral here, right? So it is an improper integral. Integral running from 0 to infinity. And I hope you remember in this case turned out to be a pretty simple thing. The improper integral always can be denoted as always is a limit of a definite integral. Okay, so using a small substitution, we get an antiderivative as negative e to the negative t. T is replaced with the upper bound b and the lower bound 0. When t is replaced with the lower bound 0, it tends to be very simple. It's 1. Okay, it is minus negative 1. And then when t is replaced with b, e to the negative b, put in another way, you may want to, because b is approaching to infinity, it's positive. So put in another way, you may want to consider put the exponential term to the denominator. And then the exponent tends to be positive. So it's easier to say, as b is approaching to infinity, negative 1 over e to the b, it is just 0, right? Because the numerator is fixed, the denominator keeps getting bigger, so it's 0. And the second part we already explained, that's 1. So this improper integral, it turns out to be 1. It turns out to be 1. Okay. And now we take a look at some similar situations. How about the improper integral of e to the negative 2t? Basically, it follows the same idea. You are still going to get the antiderivative and consider the limit of the antiderivative. And certainly using the fundamental theorem of calculus, you are going to take the difference of the antiderivative at the upper bound and lower bound. And at the upper bound, we are having a similar situation. Okay, it is e to the b. Numerator, it is fixed. Denominator keeps getting bigger. And also, this negative 1/2 comes from integration by substitution. It also applies to the lower bound when t is replaced with 0. Okay, so we do have this minus negative 1/2 here. E to the 0 is 1. So it tends to be plus 1/2. This part of limit tends to be 1/2, tends to be 0. So overall, this time we get the improper integral as 1/2. And hopefully you can give a try, like e to the negative 3t, you're going to get 1 over 3. E to the negative 4t, you're going to get 1 over 4. So I said in general, if we consider the improper integral of e to the negative st, these 1, 2, 3, they are being replaced with s. Let's assume s is positive. So in the end, we figured out the integral, it is 1 over s. It is a discussion of improper integral. And indeed, I want to tell you, Laplace transform, indeed, it is defined as an improper integral. So here's the formal definition. The transform, it is a transform of a function. So it is the improper integral of e to the negative st times the function. And also keep in mind, an improper integral could be convergent or divergent. Convergent simply means the improper integral, it is a fixed number. Divergent is really, it's nothing, it's not a fixed number, okay. So if the improper integral is convergent, and I hope you can tell from the calculation I did here, because we do have s as part of the exponent, e to the negative st. So in the end, we should have a new function involving with s. So I write the result as f of s, okay. In case, well, if this improper integral is divergent, And indeed, if you may wonder if the improper integral is convergent or divergent, indeed, it turns out to be in many situations. Okay, the improper integral, it is convergent. It is convergent. So let's take a look at some simple cases. Let's consider when the function it is 1, and the improper integral, the Laplace transform, it is calculated as the improper integral from 0 to infinity e to the negative st times the function times 1. So indeed, this is just the previous example as I just calculated. And the Laplace transform of this function 1, constant 1, it tends to be 1 over s. Laplace transform of 1, it is 1 over s. And then, well, what about some linear functions? And we are just consider this function as t. So this time we consider the Laplace transform of t. Again, according to the definition, it is the improper integral of e to the negative st times t. And this time it is a little different. And the first, what I did here is, really I want to tell you I'm considering integration by substitution. Remember, integration by parts. This is the formula. Antiderivative u dv is uv minus antiderivative v du. So I'm trying to match the improper integral in the fashion of u dv. U is t, okay. dv or v, it is e to the negative st. If you wonder if they are really the same or not, I would suggest maybe go backward. D of this exponential term, it is a differential, right? Differential of this exponential term. So which would be the derivative times dt. The derivative, it is negative s times e to the negative st. The negative is cancelled by this negative 1 in the front, and the extra s is cancelled by the s in the denominator. So I'm saying those two integrals are really the same. They are the same. I hope you see that. Then, as I'm saying, the purpose for me to doing this manipulation is that I'm using integration by parts. According to the formula of integration by parts, I kept this negative 1 over s in the front, so I should have u times v. As I'm saying, this is u, t is u. The exponential term is v, so tu times v minus antiderivative of v du, okay, e to the negative st dt. And certainly this improper integral, actually this is an improper integral, it is always a definite integral. So we do have the lower bound, upper bound, lower bound, upper bound for each. Okay, and then for this improper integral here, as we calculated earlier, it's 1 over s, right? It is 1 over s. And also the interesting part from this part, this thing here, okay, t times e to the negative st. Again, you may want to consider this is t over e to the positive power. And then you may want to say, indeed, if you can convince yourself, certainly when t is replaced with 0, I say the term, it is approaching to 0. That should be fine. T is infinity approaching to infinity, that is also approaching to 0. And you may want to give a try yourself. You can show this entire limit, okay, the entire thing, it is 0 by using the L'Hopital rule. So in the end, the improper integral, or really I'm talking about the Laplace transform of t, it turns to be negative 1 over s times parentheses 0 minus negative 1 over s. It is 1 over s squared. So that is the Laplace transform of t. Or mostly I'm thinking about the polynomial functions or power functions. We got the transform of 1, we got transform of t, kind of a little bit of situation. Transform of 1, it is 1 over s. Transform t, that's 1 over s squared. And then maybe you want to take a guess. Transform t squared would be 1 over s cubed. Indeed, I would say it's a good guess, but there is a little difference there. Okay, so let's take a close look how we can calculate the Laplace transform of t squared. According to the definition, the transform, it is always an improper integral of the same exponential term times the function. And this time, still I am doing integration by parts. Indeed, I'm doing integration by parts 2 rounds, if you see it clearly. Okay, I'm trying to match the integral in the fashion of u dv. Then I can use a formula like this. Okay, so you take a look if these two are the same. And still, I would suggest you go backward. It's easier to go backward because this denotes a differential of the exponential term. And according to the chain rule, there's negative s, which will cancel this negative 1 over s. Then remaining part turns to be the expression in the middle there. Okay, so these two are the same. And then using integration by parts, this time u is t squared, v is the exponential term. So using integration by parts, I'm getting such, and minus the integral from here. And you can take out this 2 here. So this is really the integral of the Laplace transform t as we just calculated. That's 1 over s squared. So in the next round, this integral it is simply replaced with 1 over s squared. And certainly there's still 2. So it turns to be 2 over s squared. And also you want to take a look. This time, what we are having here is t squared times the exponential term. Really the exponential term, because of minus sign, it is in the denominator without a minus sign. So you can use the L'Hopital rule. Maybe it will take 2 rounds of L'Hopital rule. You will see the limit as t approaches to infinity of this function, it is 0. Certainly when t is 0, this is still 0. So in the end, what I figured out here is if you guessed from the transform of t and the transform of 1 and transform of t squared, you guessed s cubed in the denominator, but still there's another extra 2 on the top. Extra 2 on the top, okay. And also I'm writing this as 2 times 1 because I really want to tell you this is 2 factorial. Certainly 1 is 1 factorial. And also I just want to mention another quick thing. 0 factorial, it is 1 too, okay. 1 factorial is 1, no doubt. But anyway, 0 factorial, it is still 1. That is the way it is. 0 factorial is 1. So I'm saying, when you look at the Laplace transform so far, what we did, the transform of 1, which is now, say, you want to consider t to the power 0. That's 1 over s. Transform of t to the 1, that's 1 over s squared. Transform of t squared, that is 2 times 1 over s cubed. Actually, I did show the work of the transform of t cubed. I guess I'm not going to read this entire thing. And really, if you are watching the video, you want to pause a little bit and make sure if you are fully convinced what I left here. And according to my calculation, the transform of t cubed, we do have s to the 4. Then the top, it is 3 times 2 times 1. I say that is 3 factorial. And then if you wonder what the pattern would look like or what you may expect for the transform of t to the 4, I say the transform of t to the 4 looks like we are going to have s to the 5 in the denominator. Then the top would be 4 factorial, 4 times 3 times 2 times 1. So indeed, we do have the generalized formula for the Laplace transform of power functions. T to the n, it tends to be n factorial over s to the n plus 1. And don't forget that this is a small trick. 0 factorial, it is 1, okay. 0 factorial, it is 1. And I say I did some calculation about the Laplace transform of those simple power functions. And also, I suppose this really would be easier using the integration by substitution. Laplace transform of e to the at, it can be derived as 1 over s minus a. For example, if I have the Laplace transform of e to the 3t, that is 1 over s minus 3. Laplace transform of e to the negative t, because a is negative 1, so it is 1 over s minus negative 1, which just turns out to be the 1 over s plus 1. So now we are having Laplace transform of those power functions, exponential functions, and also we do have Laplace transform of trigonometric functions. But anyway, I'm going to skip the discussion how we get the Laplace transform of sine and the cosine. I'm just going to present this result here. Okay, Laplace transform of cosine kt, like 2t, 3t, oh yeah, these things, it will be s over s squared plus k squared. Laplace transform of sine kt, k is any number, could be 2, could be 5, or could be 11, could be 100, those things. So it turns out to be k over s squared plus k squared. And also we have little more formulas. The Laplace transform of t to the n, the combination of power function and the exponential function, and then combination of the exponential function and the cosine, combination of exponential and the sine. Okay, and all these formulas, they are summarized on the table 8.1.1 on the textbook, page 472. So how about before we take a break, let's take a quick look if we do understand especially those 3 last formulas. So I'm having the transform of t to the power of 3 times e to the negative 2t. So clearly it's going to match the first formula right here, right? And the 3, a is negative 2. So 3 factorial, the transform is 3 factorial over s minus negative 2, s minus a, but a itself is negative. So s minus a tends to be s plus 2 to the power 4. How about the combination of exponential and the trigs? E to the 5t times cosine is 7t. So a is 5, b is 7. And s minus a, s minus 5 over s minus a squared, s minus 5 again, but the squared plus b squared, b is 7, that's 49, right? Laplace transform. And the Laplace transform of e to the negative t sine 2t, so a is negative 1, b over s minus a squared plus b squared. Okay. A is negative 1, s plus 1 squared, and the b is 2, so that is 2 over this s plus 1 squared plus 4. The Laplace transform. And again, in general, the Laplace transform, it is defined as an integral transform. It is an improper integral. This is improper integral. But anyway, for the sake of our class, it is really not required to use the definition to calculate the transform. What you really need to know, it is really the formulas summarized on the table 8.1.1 on the textbook, page 472. You do need to know the transform of power functions. For example, t to the power of 8, then you would have 8 factorial over s to the 9. And if you need to know the exponential function, e to the 8t, if e to the 3t, that is 1 over s minus 3. If it is e to the negative 2t, that will turn to be 1 over s plus 2, because minus negative 2, it is plus 2, right? And also we do have the transform of cosine and the sine. And then more importantly, we do have the transform of the combination of exponentials and the powers. Power function and the exponential function. Exponential function with cosine, exponential function with sine. Okay, we only need to be able to identify the Laplace transform of given functions using those formulas. It is really not required to calculate the Laplace transform using the definition. Certainly, I think the definition it is very helpful to understand the Laplace transform. But anyway, to find out transform, you do not need to worry about too much about improper integrals. You are going to know those formulas very well, and especially the last three. So this is the first part for Laplace transform. Thank you for watching.